In this video, we'll be talking a little bit about the chi-squared statistic and how you might use that in Physics 472. But first, before we talk about that, I'd like to talk about regular random distributions, in particular the Gaussian distribution, and just review something that I'm sure you're aware of. If I have a variable x in a Gaussian probability distribution for x, then it's centered around the true value x naught. Okay, then there's my version of a Gaussian. And you're familiar with, of course, that there's the central value of the Gaussian, and it has some width associated with it, sigma, which if we have a bunch of data that we think follows a distribution like this, we'll estimate sigma often as the standard deviation. But let's say that we've measured n equals 1,000 samples from this distribution, so we've made 1,000 measurements of something, and we go and we calculate the mean. Okay, x bar equals 1 over n of the sum over all the samples, right? And we get the mean, right? And we get our estimate of sigma, which is another sum having to do with 1 over n minus 1 of blah 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 blah, which you can go look that up. The important thing is that we use those 1,000 samples in order to estimate the mean, and then we're going to report that mean. Okay, and we want an error on the mean, and the error on the mean often is given this, or at least I like this the symbol sigma mu, because some books actually call this the mean, mu. And sigma mu is not the standard deviation of the population, because our estimate of the mean gets better and better as we measure more and more data points. Okay, if we took 1 million data points, we'd get a better estimate of the mean. But instead, sigma mu is given by our estimate of the standard deviation, or of the population sigma, so our estimate of the standard deviation, and we divide that by the square root of n. So this is the thing that we should report as the error associated with our mean that we calculate from our measurements. Okay, if we do this for a bunch of data, okay, so let's actually pretend that we've made a whole bunch of measurements, and so say this is now some variable x, and this is a measurable thing y, and we measured just a bunch of data here. So we've got at various values of x, we've got various estimates of y that include error bars. And of course, in this case, you'd look at it and go, boy, I want to fit a line. So we fit a line to this, and the line would look something like this. Okay. And first of all, how do we fit a line? How do we decide which line is best fit to these data? Usually, people minimize what's called the chi-squared statistic. So the chi-squared is given by, you take the sum over all the data points, and you take the value y sub I minus the model that you have for that value. So I'll call it m sub I, and you square it, and then you divide that by the error bar squared. So let's notice a few things about this. First of all, I have to have a model that tells me what m sub I is. Okay, so what do I mean by m sub I? What I mean by m sub I is, there's a model prediction at this value of x right here, and another model prediction here and here and here is on the line. Okay, in other words, it's the value of y on the line at that value of x. That's my model prediction. Now, my model could be more complicated than a line. It could be sine waves or polynomials or other fancy functions, right? But the point is that the model has some prediction of y at that value of x, and that's what I stick into this spot right here in the chi-square. Another thing to notice is that we have squared quantities, a squared deviation. In other words, data, the mean that I reported, or the value of the data point, minus the model, that's a deviation squared over the sigma squared. That keeps the units nice. So whatever units my quantities have, they get canceled out and calculated in the chi-squared, which is a nice thing. Another thing to notice here is that I'm having a sum over all the data points, And, on average, I kind of expect the deviation to be of order the same size as sigma, So you'd be, pretty reasonable to say, I think I'm going to get about 1 from each of these terms in this sum. So therefore, I kind of expect chi-squared to be equal to, roughly speaking, the number of data points. That's not quite true, because if you imagine taking a line like this, so let's actually redo this exercise, and I'm going to fit to 2 data points, okay? If I have 2 data points, my best fit model for 2 data points is, of course, going to be a line that passes exactly through those 2 spots, right? And here I'm going to get chi-squared equals 0. Well, that happens to be that I'm fitting a line, so I have y equals mx plus b. I shouldn't use the letter m, but that's traditional slope, so maybe you want to call it a or something. But there's a parameter and there's a parameter. There's 2 parameters. So in other words, I use up 2 degrees of freedom in my fit, okay, because I've got 2 parameters, 2 independent parameters. So in fitting a line, I really expect chi-squared to be more like n minus 2, or in general, n minus the degrees of freedom that that are in my parameters. Okay, so n minus the number of parameters. This has a special name. This name is called the degrees of freedom, the total degrees of freedom. So I took out 2 degrees of freedom in my fit, but n data points minus those is equal to the number of degrees of freedom, and often this is given by nu as a symbol. So in all that we do from now on, we're going to talk about nu being the degrees of freedom. Okay. All right. So let's look at this. Again, I'm going to look at a fit like this. Here we go. We'll draw it again, x and y, and just sketch in some data points. Okay, and we do the fit. And what you notice is, of course, that in general, if you look at a fit in some data, you may see that the line actually misses some of the error bars sometimes. Well, that's a good thing. Okay. And the reason for that is that if I have a Gaussian probability distribution, okay, so I'm just going to draw this like this, and the true value is given by this point right here, I expect to be able to be within 1 sigma, the size that I traditionally plot my error bars. I didn't do a very good job of making that symmetric. But let's say that's the plus and minus 1 sigma part of the probability distribution, where this is the value of y and this is p of y. Okay. I expect to be in this area about 2/3 of the time, and out on these tails, the combination of the 2 tails, about 1/3 of the time. So about 1/3 of the time, my line should miss the error bars, and about 2/3 of the time, it should go through the error bars, roughly speaking. This is more true when you have more data points. It's your error bars aren't always Gaussian; they're not always symmetric. But as a rough idea, this is a reasonable thing. Doing this while just looking at a plot is given the derisive name of chi by I. Okay, and lots of people belittle this, but you know what? It's actually a pretty good technique. It's especially good just as an order of magnitude. Hey, is that plot crazy or not? There are cases where the errors or data points are correlated, where this won't give you a very good answer, but often it's a great tool. I've seen a lot of lab reports where the data that somebody returns looks like this. Okay, I've got a data point and another data point and another data point and another data point. Okay, and you just look at all these data points and then you look at the fit line that goes through them, and it's just like passing ridiculously close, like within 1/100th of a sigma to all those central values. And in this case, if you make a plot and see it like this, your brain should be screaming at you, uh-oh, that fit is way too good, there's something wrong. And usually this means that the error bars are too large. You've overestimated the error bars. Sometimes maybe you're plotting sigma instead of sigma over square root of n, for instance. That's a very common error. So if you can avoid that, that's great. If you look at it and you say, oh, I've got the opposite case where y is a function of x, it looks like, oh no, I've got, like this, and then this, and then this, right, and then this, and I'm trying to fit a line to it, you know, we all know that what that means. That means, oh, you know, there's something else going on. Maybe your model's not good, right? Or maybe your data's corrupted or something. So doing the chi by eye at least steers you in the right direction of looking for things that might be going on. Now, of course, we can actually calculate the chi-squared statistic that I wrote down on the other page. That is a good thing to do as well. So let's talk about that. I'm not going to write down the actual formula for it because it's just too complicated, okay? But what I do want to say is that the chi-squared, as I said before, is equal to the sum of these deviations. I'll write it as xi minus mi this time. Quantity squared over sigma I squared. This is in the case if I'm measuring x. And the probability distribution for this depends on the number of degrees of freedom nu. Okay? You're going to sum over n data points here, right? You have, let's call it little n fit parameters. Okay? So in general, nu will equal n minus little n. So this is the number of data points. This is the number of fit parameters. And this number is the number of degrees of freedom. And the chi-square statistics probability distribution, in other words, p of chi-squared, requires that you also know the degrees of freedom. Okay? So, in other words, if I, which, you know, is kind of related to the number of terms in the sum, so I sort of, we expected that, right? So the interesting thing about this is that for small numbers of degrees of freedom, okay, so let's say you have nu equals, 2 or something like that, the chi-square distribution peaks sort of somewhere near 2. Okay, there's 1, 2, 3, 4, right? But it's got some big tail going out like this, and it's asymmetric because it can't go below 0. So for small numbers of degree of freedom, it's going to be asymmetric, and it'll peak somewhere near this, but it's pretty wide. If I have nu equals 100, okay, nu equals 100, well, you know what, I do expect it to peak out near 100, and you know what, that probability distribution is actually, you know, it looks an awful lot like a Gaussian, centered out at 100, okay? So the important thing to know here is that I expect it to peak near, you know, the chi-square distribution should peak near a nu, but there is a width to that distribution, okay? There is some width here or here, right? And so I shouldn't be too surprised if I don't get exactly nu for my chi-squared. In other words, probability insists that that's going to vary around some. So there's another statistic that I'd like you to know how to calculate, which is to look at this probability distribution, say this one down here for 100 degrees of freedom, and to ask, is the value of the chi-squared that I got for my 100 degrees of freedom, say my 102 data points minus 2 fit parameters, is that value crazy or is it reasonable? And my value could be that it lies right here, or it lies right here, or maybe it lies somewhere reasonable in that distribution. And the statistic that we use to say something about this, well, there's two ways of putting it. One is called p greater often, and a complementary one is called p less than often. And what p greater than is the probability that I would have gotten my value of chi-squared or larger. My chi-squared or larger. Okay. P less than is that I would get my chi-squared, the one that I came up with in my measurement, or smaller. Okay. So let's look at this. Actually, let's draw a brand new distribution and talk about this. Okay. All right. So here is the value of chi-squared for, we're going to say, 30 degrees of freedom. And here is the theoretical probability distribution of p chi-squared for nu equals 30. Okay. And I'm going to wing it here, and I'm just going to say it's something like this. Okay. Right. And of course, course, never formally goes to 0, right? And let's say that my value of chi-squared that I got was 32 or something. And don't compare this to a real distribution because I'm making up the curve here. All right, so what is p greater? P greater is this area right here, okay? And if I got, of course, if my chi-squared was right here, then it would be all the area above it, right? So what does this mean? This means that if p greater is equal to, see daisy, if p greater equals, close to 1, well, that means you're low on the probability distribution, right? If it's, anywhere from 0.1 to 0.9 or 0.01 to 0.99, depending on your taste, that's totally reasonable, okay? If it's like, really close to 0, say you get a p greater of 0.0001 or something like that, right? That means that you're way up here on this tail. In other words, if you do your experiment many, many times, it's very unlikely that you're going to get a chi-squared so high. If you're way down here, it's very unlikely that you're going to, in random trials of the experiment, get a chi-squared that's so low. Okay, that's what I mean by close to 1. Say you got 0.99999, right? Then you're way off down here, and it's unusual, right? You don't expect it, statistically speaking. So if you calculate p greater, and you find either this or this, right, then you should kind of ask yourself what's going on, right? In the case of being up here, what that means is that your deviations are bigger than your error bars explain. If you're way down here, the error bars are bigger than the actual deviations that you saw, right? And so you have to sort of think about whether you're making a mistake somewhere if you see either of those cases. P less than is really just equal to 1 minus p greater, right? So they're complementary statistics. Okay. All right, so in MATLAB actually has a function that will allow you to calculate this. And I actually forget exactly what the name of the function is, but if you look up probability distribution chi-squared, you'll be able to find it. I've actually, I was playing with it just a little bit ago, and I've totally forgotten what it is now. So anyway, you can look it up. But MATLAB will make it very easy to calculate this if you know what your value of chi-squared was, your measured chi-squared, right? And if you know what your degrees of freedom was. So please go ahead and do that, and I hope that this has been helpful. Feel free to do chi-by-eyes. Feel free to be critical of your error bar sizes. And please do calculate the chi-squared when you have data with error bars. Thank you. Final note, I actually just went and looked up MATLAB functions to plot a chi-squared distribution, or to calculate a chi-squared distribution itself, okay, this thing right here. You can use the function chi2 PDF, which you'll need to tell it how many degrees of freedom you give it. And to calculate p greater, you will use the function chi2 CDF for the cumulative distribution function. And then what you do is you hand that your value of chi-squared, the new, you should check the arguments here, and then you tell it you want the upper value, because without this argument upper, it actually calculates p less than, okay? So anyway, you can play around with that. P less than also chi2 CDF, chi-squared new, and you don't have to hand it the argument for upper. All right, have fun.